And then there's a lot of ways we can calculate energy based upon an equation. We're going to show you several different ways to do that because sometimes one way works best, other times another way works best. So I'm going to show you about 3 or 4 different ways to calculate the same value depending upon what kind of information that you have. And then we are going to talk about the changes of our states as we add energy. And the 3 states that we use in chemistry are solid, liquid, and gases. Each one of those requires an amount of energy being added or taken away to change from one state to the other. And that becomes a long calculation. Not that it's any more difficult, but it just is long and detailed. I see the rolling of the eyes in the front row. Long and detailed. Okay. Now, energy. E. Ultimately, energy value is E. We're going to change that a little bit as we go ahead. But to remember what an energy unit is, it is a joule, which is 1 joule is 1 kilogram times a meter squared divided by a second squared. Right? And so we will be using joules. Now, what is the energy value unit in the U.S. system, the English system? A calorie. All right. And there are calories and there are calories. Okay. A calorie that you see on, let's say, your Snickers bar, that's 783,000 calories that you have in that Snickers bar. Okay. That is a capital C nutritional calorie. Okay. Which is 1,000 little calories, which is a chemical calorie. Oh my gosh. And so we may have to use calories at some moment in time, but the SI unit is joule. And if you go overseas and you look at the nutritional things overseas, you will see kilojoules as the energy value. All right. Here is one thing. We got to think about energy, okay? And when we talk about energy, here's where flow comes into place. There are 2 places in which energy can come from and go to. One is called the system, and one is called the surroundings. The system itself is the part of the universe that we are interested in, the actual chemicals that are reacting. The surroundings is everything else. The water that it's in, the container that it's in, the room that it's in, the air that it's in, the earth that it's on, and the entire universe is the surrounding. Okay, you got the system, I'm focusing on that, and then you have the universe, the surrounding. Between the 2, energy will flow either from the system into the universe, or into the surroundings, or from the surroundings into the reaction. So we are measuring the movement of that energy back and forth. The first law of thermodynamics says that energy is neither created nor destroyed. It must be conserved. This sounds very much like the law of conservation of mass. Einstein created a little equation, okay, where we said energy can't be created nor destroyed, mass can't be created or destroyed in a chemical reaction. Einstein had a little bit of issue with that, and he did this: E equals mc squared, where we have energy, we have the speed of light, and we have mass. Mass can be converted directly into energy. So the best way to describe what truly happens in the universe is there is a law of conservation of mass and energy. Mass can be lost based upon this Einstein's equation, but it is converted directly into energy. And so if we add up all of the energy and we add up all of the mass in some sort of transformation, that is constant. In chemical reactions, the mass is always constant. In nuclear processes, sometimes a little bit of the mass is converted directly into energy. That's why nuclear processes give off so much energy. And so the total amount of system plus the surroundings energy is constant. And we just transfer, vice versa, back and forth. Okay, got that? Now, here's the problem. For us to know absolutely what the energy value is on anything, we would have to know the absolute amount of energy in the system, in the reaction. We can measure that really, really well. We can measure the system and get it to a very high degree of precision and accuracy. But to know what the absolute value of energy, we would also have to know the entire energy of the surrounding universe. That is a number that we cannot get. Okay? So we can't actually calculate true values of anything because we don't have one of the whole values known. We only have one of the values known. So what we do is this. We always measure energy in terms of change. Okay? What is the symbol for change in chemistry and science? The delta, the little triangle. Okay? So the change in energy is equal to the energy of the system final minus the energy of the system initial. Final minus initial. Now, remember when we calculated the energy of transition from one Bohr level to another orbital? You had an equation that you could either do final minus initial or initial minus final, and you had to remember where a negative sign was or not. Everything else in chemistry is final minus initial. Oh, you probably should look up that equation because that might come up on the final exam. Okay, so I like to learn everything final minus initial because all calculations are done that way. Almost all calculations are done that way in chemistry. And so we measure the system really, really accurately at the beginning, really, really accurately at the end, and we see how much changed over a short period of time. And so what we're going to do is we're going to look at the change in energy. Now, the change in energy of any system is dependent upon two things. Okay? Heat is going to move, and work is going to be done. Okay? Those are the two components. There's energy and actual flow of heat from one place to the next, and there is some energy that is lost in terms of work. Okay? Now here, we're going to simplify this for G-Chem. P-Chem gets really complicated, but we're going to simplify this down. Now, let's think about this. What is work? Well, it's a force times a distance. Okay? Now, let's just say you add a solution of silver chloride and a solution, a solution of silver nitrate and a solution of sodium chloride. Put them together. All right? You mix them. A reaction occurs. You precipitate out silver chloride. How far did that test tube move because of the reaction? Did the test tube get up and walk a certain distance because you mixed the two solutions together? No. In most general chemistry reactions, the distance that is moved is 0 times any number equals work is going to equal what? Equal 0. Okay? So, for most G-Chem, work doesn't matter. Why? Because the distance is 0. The change in distance is 0. So that means I can say the change in energy is equal to the change in work. Now, one thing about general chemistry, okay? most reactions, what in the world? Reactions are done at a constant pressure. And this is important. What is the constant pressure that I'm doing the reaction in? If I take those two solutions, I mix them together, the pressure is the atmospheric pressure. It doesn't change during my reaction. That's not part of the reaction itself. Okay, and so this defined heat at a constant pressure has another name. It is called H, which is called enthalpy. Enthalpy. Okay? So what happens is the change in energy is going to be the actual change in enthalpy, which is heat at a constant pressure. So from this point on, if you look in textbooks, very rarely will they actually use delta E in their reactions. They'll use delta H, or enthalpy values, because in most general chemistry settings, almost all that we show you, we will never change the work in terms of a real calculation, and we won't be under different pressures. When you actually do work and you actually have different pressures, it becomes complex. You start to have to use calculus, and we wait till your senior year to start doing those kinds of things too. Okay? So we're going to not go down that road. Now, I will make you think about it in simplistic terms. And this is where reading something technically becomes a problem. All right. There are two flows of energy. One is endothermic, and one that is exothermic. So these definitions are important. Endothermic means energy is absorbed from the surroundings into the system. The system, the reaction itself, will take energy from the surroundings and pull it into itself. It absorbs it. Technically, if by chance you had an endothermic process going on in your hand, it would feel cold because your hand is the surroundings. The energy flow from your hand into the system. It would feel cold. That's an endothermic process. An exothermic process is you put something in your hand, it is going to give off energy. It will transfer heat into the surroundings. So if I held on to something that was exothermic, it would feel hot because more energy is being released. An endothermic process means that the heat, okay, would be gained. So the system gains heat. It also means that work is done on the system, and that would be positive. And delta E would be, I actually took in energy into the system, and it would be positive. An endothermic process means that heat would be lost by the system, given off. That's what a negative means in terms of energy. It means that work is done by the system. The system has to do work, so it has to give off energy. That's a negative sign. And then if you add the two values together, then the delta E, if it becomes negative, means that energy was lost, okay, by that system. All right. What in the world does this all mean? Change in energy is equal to Q plus W. Okay, using the rules, what would be the change in energy of this system that you just looked at? Okay, and so you have to interpret. All right, So work together, look at the rules, figure it out, come up with a guess. No, come up with a hypothesis. We're going to hypothesize this. Okay, wake up. All right. So, important words. Okay, internal energy for process in which the system. Okay, here's an important words. Absorbs. The system absorbs this heat from the surroundings, and then it does on the surroundings. Okay, the system absorbs heat from the surroundings and then does work on the surroundings. Okay, now you have to go back here for a little bit. And you got to flip back and forth. All right, so which one? Discuss amongst yourselves. So system absorbs. And does. So, okay, I'll help you out here. Change in energy. Okay, this number goes right here, joules. This number goes right here. No, that's not that number. That number goes right there. This will equal delta E. That's good. But what do you put there? And what do you put there? A plus or a minus?
Plus in front of 140 and a minus in front of 85.
A plus in front of this and a minus in that. Get out your calculators. What will the answer be?
55.
55. Okay. This is not hard. Can you add a 140 and subtract an 85? Sure. What was hard? Determining which one had the plus and which one had the minus. How many combinations of plus and minus do you have? Way too many. Actually, a good 4 choices. A, B, C, and D. On the exam. Right? And so if you read this one, absorbs 140 joule from the surrounding. Okay? Absorbs 140 joules from the surrounding. All right? The heat, system gains heat. Absorbs is gains from the surroundings. That's where it's getting it. Okay? So that one is a little bit straightforward. The other one says, does 85 joules on the surroundings. So, this one, it's positive if work is done on the system. No, this was on the surroundings. So it must be negative because the work is done. Okay, here it says by the system, but by the system on what? On the surroundings. So, do you see? It's interpretive. You've got to understand what it's saying because the math is way, way simple. That's not the hard part of this one, is interpreting what is said. And it can be said so many different ways. It's all referencing from where to what. In this case, you have to think about between the system and the surroundings. All right? So, if you're given a problem in Chem 21, You need to see and understand this page and understand what it means so you can interpret the right thing. That's all well and good when you're doing it on CHEM-111. What if you get a problem like that on the exam? What must you know? That page. And you need to know the words. And that's always good, but you have to understand what it's doing. This is where maybe, I don't know, the TRQs might have some of these things about saying it in different ways so that you can come up and be able to interpret, is it positive, is it negative? I don't think there's a real easy way to do this other than getting it into your head and thinking about it and doing examples. But, you know, this is quite a lot of work for, 3 or 4 points on the exam. But 3 or 4 points, every one of them are important, right? Uh-huh. Very important, each one. Oh, check that out. It was all done for me. All right. Now, first law of thermodynamics says I can't make it, can't lose it. All right. And here's what we do. We always measure final minus initial. So what you're really doing is this. The calculation depends only upon where you start and where you finish. It doesn't matter how you got there. Okay, give you an example of a state function. I want to go to Hammond and place mall. Right. I'm going to head to Hammond and place mall. So, I'm in Cleveland. So, I get on I-75 and I go south. We're about, let me see, what?
20 minutes.
Yeah, 20 minutes. Right. And I'm at Hamilton Place Mall. No, I'm at the exit for Hamilton Place Mall. It's another 20 minutes to actually get to Hamilton Place Mall from the traffic. Okay. All right, that is one way to get Hamilton Place Mall. Or I can get on I-75, go north, all the way up to Knoxville. Then I can get on I-40 west, go to Nashville. I can then take I-24 south, come down to Chattanooga, and take I-75 north for a couple miles, and get off at Hamilton Place Mall.
And I'll still be in the red light trying to
You'll still be in the red light trying to get there. Doesn't matter. I still went from Cleveland to Chattanooga. Okay? And I would measure initially where I went, where I started, final where I ended, and the distance would be a certain amount. I could go all the way around, and my initial and my final would be exactly the same place. So it doesn't matter how we get there. It matters the initial state, the conditions, and the final state conditions, and that's what we're looking at. Okay? And so that is dependent, that's what a state function is. It doesn't matter how it got there. All right? I can get to water at 25 degrees by cooling boiling water or heating ice water. It just depends upon those two states. All right, so this enthalpy, I've already told you we have no work. We only have heat, and it's heat at a constant pressure, so you will be seeing delta H's all over the place, and that is called enthalpy. It's not changing heat, but some people think about it that way. It's actually formally changing enthalpy. And so heat can either go in or out of the system from or to the surroundings. All right. How in the world do we actually do an experiment with this? Okay. I show you two different pieces of instrumentation. We're at the university. Which piece of instrumentation are you going to use in the lab? You're going to be using 2 styrofoam cups. Okay? Because we're going to be studying changes in energy. Now over there is called a bomb calorimeter. Okay, we have one of those. Okay, we let seniors use it. I'll tell you the reason why we let seniors use it in a little bit. Okay? But we let freshmen use this one. Okay, the styrofoam cups. Why? That's expensive. That's not as expensive. You can break this one. If you break that one, I really don't care. Get 2 more styrofoam cups. Okay. All right. This kind of experiment is called calorimetry. Okay. You can see heat from the term calorie in that. And so what we're going to do is we're going to measure the initial conditions of the reaction and the ending conditions of the reaction. And the only measurement I'm really going to use for the energy is a thermometer. The thermometer's going to move. If it is exothermic, what's going to happen to the thermometer? What is the final temperature going to be versus the initial temperature? It'll be higher or lower? It's going to be higher. And if it's an endothermic reaction, it'll get cooler. Okay. Why do I use styrofoam cups? They insulate. What we want to do is we want to keep all the energy change inside the cup so that we can measure what's actually happening. We don't want heat lost anywhere, and so the styrofoam cup keeps all of the energy changes inside the liquid, and we isolate it. Okay? And so we will also need to measure one other thing, how much stuff we use, because that's important to calorimetry. How much stuff you used, and then how much energy changes. All right, to understand this, we have to know a couple of known factors or a conversion factor. Okay? The simple definition of heat capacity, how much heat can I hold, is the energy required to raise any temperature of an object, formally 1 degree Kelvin, but we can also use Celsius. Because remember, we're doing final minus initial. If I take 100 degrees Celsius minus 0 degrees Celsius, I get 100. But if I change 100 degrees Celsius into Kelvin, I add 273. And I have to change 0 Celsius into Kelvin. That would be add 273. I subtract them. The 273 goes away. So the change in temperature, whether you use Celsius or Kelvin, is exactly the same because it's a difference. All right. Now, the molar heat capacity is the amount of heat that each substance can absorb per mole of substance. And the specific heat capacity is the heat capacity of 1 gram of substance. And so we might actually be given molar heat capacities or specific heat capacities. Most often, we will given specific heat capacities. And then that would be this, the amount of joules for every gram you use times every change in temperature, or you can see it written as Kelvin or degrees Celsius because difference in temperature will come out to the same value. So don't confuse yourself. You will see both Celsius and Kelvin. It is the exact same value. A lot of things have different heat capacities. This is a unique aspect for every substance that you have. And so just like everything has a density that is unique, we only make you remember one density. What is the density that we assume you know? Water. And the density of water is what? How many grams per milliliter? 1. Okay. We're also going to ask you to know the heat capacity of water itself, which is 4.184 joule for every gram for every degree change. That is the heat capacity of water. Water tends to have a very large heat capacity compared to other things. Water tends to be able to absorb lots and lots of heat and hold on to it for very long. If you've ever lived near the coast, usually the temperatures are moderated. It doesn't get as hot and doesn't get as cold as interior conditions because the water is absorbing and releasing that heat very slowly because it has a very large heat capacity. Okay, so here is the type of calculation you are going to be doing. The constant pressure calorimeter, basically the 2 styrofoam cups. Okay? The change in enthalpy, which is the heat at constant pressure, is equal to this. Q, the heat of the reaction, see that? is equal to negative heat of the solution. Okay? Remember an energy flow. If the system gives off, it has to go into the surroundings. And if the system absorbs, it has to come from the surroundings. The reaction is the system. The solution is the surroundings. They have to be negative to each other. Because if one's flowing one direction, the other is flowing the other direction. That is why the negative sign is there. Okay? All right? And either vice versa. And so you will see this equation. You have to remember or realize what you're solving for. Are you referring to how much the solution is going to be absorbing or giving off? Or are you talking about the reaction? That is interpreting what the question is asking, whether you put the negative sign or not. It is mathematically this. The specific heat is something that's going to be in a joule times a degree times a gram. So to get joules, you have to multiply by grams to cancel out grams, and you have to multiply by a change in temperature. And so grams cancel out, Celsius cancel out. You will get a value of energy in joules, and then it will be either negative or positive depending upon what you're looking at. Okay? So 3 numbers multiplied together. Solution times the grams of the solution, or the specific heat times the grams of the solution times the change in temperature. Ooh! What 2 components make up a solution? Let's go back to a solution is made up of 2 things. What? Solute plus solvent. How do I distinguish between a solute and a solvent? One's bigger. Which one is the bigger one? The solvent is the bigger one. The solute is the smaller one. Okay? So that's important. It may come up in a problem later. All right. Here we go. The specific heat of toluene is a 1.13 joule every gram every Kelvin. Here's where you can do either Kelvin or degree Celsius. How many joules of heat are needed to raise the temperature of toluene from 10.4 degrees Celsius to 28.0 degrees Celsius? All right. What in the world are we doing? Now, this equation is given you just a little bit differently. Do you see what's in this equation? There is a negative sign here. And so if I'm actually going to use this equation using that negative sign, then the solution is negative. And if you're talking about the reaction, it's positive. Okay? Now, let's decide this. Are we talking about reaction or solution? Based upon this equation, or this problem. Heat's going to flow. Where's heat flowing into? The solvent. The solvent is part of the solution. So, first of all, we know now that we're solving for this thing right here. Okay? And so, to do this, we have to multiply the specific heat. Do I have specific heat? Yes or no? Yep, right there. You have to know the grams of solution. Do you have that? Yep, right here. And then you have to have a change in temperature, which you have this and that. Okay. Now, change in temperature. The delta change in temperature is the temperature minus the temperature. Which temperature minus which temperature? The temperature what? Temperature final minus the temperature initial. Okay, so the negative Q of the solution is equal to a negative sign times the specific heat, 1.13 joule for every change in temperature. I can change that directly to Celsius because they're the same in this case, times 40 grams times, okay, what is the final? $28. What is the initial? 10.4. That would be in degrees Celsius. So the degree Celsius will change. Well, cancel out. The grams will cancel out. And what do I get? What is 28 minus 10.4? 17.6 times 40 times 1.13. You get what?
Negative 795.52.
Okay. You get negative 700 what?
795.52.
0.5 joules. And so, for the solution, you would actually need to add 795 joules to it for the temperature to go from 10.4 to 28 degrees. For it to raise, you have to add 795 joules for that to occur.